So again, we will review all the materials which will be covered by this in midterm. First, let me take any questions. Okay, any questions, homework or any classes. Any questions will be okay. Well, the first chapter was about equilibrium mostly, right? So that is nothing special, and you need to pay attention to moment definition, and chapter 2 is mostly about bar under uniaxial load, tension, and compression, and definition of Young's modulus and Poisson's ratio. Right? And as an example of chapter 2, there will be some statically indeterminate and determinate problems. For statically indeterminate, you have to solve the problem considering equilibrium, material property, and geometric compatibility. All those are 3 steps. Whereas if you have a class statically determinate, all the reaction forces can be solved using only force equilibrium. That's the difference between statically indeterminate and determinate. And we had some example, several springs in series or parallel, whatever forms. That is the key point over there. And chapter 3, what do we have? We have stress, strain, and temperature relations. Right, chapter 3. Yes, chapter 3 is also regarding statically determinate, indeterminate, and chapter 2 we define Young's modulus and Poisson's ratio. So in chapter 4 we defining material property in 3-dimensional case. Stress, strain, and CTE. What is the CTE? Coefficient of thermal expansion. In 3-dimensional case, means that we have 6 components of stress and 6 components of strain and temperature. So a body is subject to stresses and temperature, how much strain we will have. Or if strains are given and stress are given, temperature is given, then how much stress will be generated. This is very important question, and this will be one of the problem you will see in midterm. Okay, stress, strain, and temperature relations. And we define the stresses and we define strains as a continuation of defining stress. We need to understand how to transform stress. The meaning, the concept of the stress transformation is that stress is there, stress state is there, but we just rotating coordinate system, and the component will vary. Right? Component will vary, and we drove that equation. We drive the equations, and we study about the Mohr circles and how to draw Mohr circle. We define x and y, and we define the radius, center of that Mohr circle, right? And we calculate the principal stress, we calculate the maximum shear stress. And then come to a failure criterion of material. We define von Mises stress and Tresca mostly in terms of principal stress. So you have to know how to calculate the principal stress. And well, these are all subjects will be covered in this midterm. Okay? So from chapter 1 to chapter 7. Sorry, I have to correct that. So after midterm, we will study about the torsion and bending. Those are two main subjects after midterm until final. Before that, we will so anyhow, let me have any questions from you. If there is no question, well, no class. But you have to make use of this chance. The more you questions, and the more answer you will get from me. Well, we have several problems regarding stress, strain, and temperature relations. And for instance, let's say we have a two-dimensional body, okay? Two-dimensional body. If I say 2D problem, which means sigma z, sigma zx, sigma zy will be 0. So usually what I meant, two-dimension is plane stress. Sometimes we may refer to plane strain. Plane strain means that epsilon zz, zy, zx is 0. Well, there is difference between plane stress and plane strain case. Okay? So anyhow, if we have a plate or a two-dimensional body with a constraint on each side, and then subject to delta t. You had this one as a homework, right?
Yeah.
And delta t increased. And what happened to this body? If there is no constraint, no constraint, this body will expand this much, right? Freely expand. But this side wall will constrain this body such that it won't deform, which means that externally there will be a compressible load, right? So you need to understand this way. If there is some constraint and temperature is increased, then the side wall will compress this body such that the final deformation, the body will not deform. Anyhow, how do you solve this one? Meaning how to calculate the stresses inside the body. The key word here is that since we have a constraint, that means epsilon xx, epsilon yy, and epsilon xy is 0, right? That is the first step you have to write down. Because of a side wall and constraint, this is a conditions in equation. Now, what is the next one? Next one is the stress-strain relations. What is that? always I would say strain equal Sijkl stress. Well, I never use this equation. Oops. Well, it just a little complicated equations here, but conceptually there is the strain and stress and delta T here. So in one-dimensional case, we have a strain equal 1 over E, right? 1 over E and sigma. This is the strain due to load, due to stress, right? A bar will be extended when you apply load. And there will be another deformation caused by delta T, right? So 1 over E, you got to remember this, 1 over E. See, if we look at this one, you have a sigma equal E epsilon. But remember, when you consider stress and temperature, you have to add them, you have to add strains. This is a strain due to stress. This is a strain due to temperature. You have to add them. Add the strain, okay? Remember, add the strain. Anyhow, let's try to solve this simple question again. See, one-dimensional case, and you have a constraint, and which means that strain in x directions equals 0, right? And from here, strain equals 0, and stress will be simply E alpha delta T. And here, pay attention, there is minus sign there. Why? That means this bar will subject to a compression, right? So if there is no constraint, this bar will expand this much. How much expand? Well, simply alpha delta T. This much expand. And how much we apply? A compressive force. We have to apply some force here. And simply this is a strain. And we apply sigma equal E alpha delta T. That's the stress we need to apply to back into this amount, into original positions, right? That's what it means. And let's say this material fails. Well, if this is a sigma yield strength, this stress, compressive stress, might reach material yield strength. Well, that is compressive, but still material can fail or yield. How much delta T you need to cause material failure? Well, simply E alpha sigma yield, right? This is the temperature you need to apply to cause material failure. Right? Okay. Well, this is a one-dimensional case. You can have same type of questions in two-dimensional case. Let's say you apply delta T, and let's calculate the strain, epsilon xx, epsilon yy, and we have the 1 over E, Poisson's ratio, minus Poisson's ratio, and 1 over E, and sigma x, sigma y, and plus alpha delta T. Alpha delta T. Like that. Well, I didn't consider the other terms because simply sigma zz, sigma zx, sigma zy, and also I didn't consider sigma xy. Why? Why didn't I consider sigma xy? Because there won't be no shear stress, right? Because only a temperature is applied, and so there is no sigma xy. So anyhow, this is the two-dimensional case, and when you apply delta t, and as it says, constraint meaning there is no strain, which means that this term will be 0. Right? Yes?
Yes.
Okay. So you can simply calculate. You can calculate stress, sigma x and sigma y. You just inverse this matrix and you apply 1, 1, alpha, delta t, and you can simply inverse this equation. Right? 1 over e minus e. Well, 1 over e can be out. So this will be 1 minus Poisson's ratio minus Poisson's ratio and 1 inverse of this one. Right? And how to invert this one? Well, you simply determinant will be 1 minus mu square, right? Well, you can easily invert the matrix. Anyhow, that's the compressive stress. There is the compressive stress here. And you calculate the stress. Now, how much the delta T, which will cause the material failure? Well, you simply apply von Mises yield criteria. Right? So sigma x, sigma y equal minus 1e and 1 minus mu square and 1, 1. Here is mu equal again 1, 1 alpha delta t, right? This will be a compressive stress. And what is the von Mises stress for this stress state? Well, sigma von Mises stress is simply, okay, before we getting von Mises stress, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square, sigma 3 minus sigma square equal 2 times of sigma yield square. This is the von Mises yield criterion. And this case, we have only non-zero stress, sigma x and sigma y, which will be a principal stress. So sigma 3 will be 0, and sigma 1 minus sigma 2, well, as you can see here, sigma x will be same as a sigma y. Right? So this term will simply disappear. But we still have this term and this term. So twice of sigma yield square will be twice sigma y square. Am I right? So then simply sigma 1, whenever sigma 1 reaches sigma yield, then the material will fail. So what is the each terms? Well, this and this. Sigma x will be minus 1 over e alpha delta t 1 over mu square 1 plus mu. Right? And which will be minus e alpha delta t, and this one 1 minus mu, and should be same as a sigma yield. And as you can see, delta t equal whatever value. Right? Well, as you can see here, we do have a Poisson's ratio. Okay, let me see. In one-dimensional case, the value was a sigma x. Sigma x was, how much was it? Oops, there is something wrong. There is something wrong. Okay, 1 over e, it needs to be inversed too, right? See, here is 1 over e. 1 over e needs to be inversed. And so I should be, sorry, this is not right. It should be E, and it should be E. So as you can see, E alpha delta t minus Poisson's ratio. Remember this one? This term? What was this term? This term was a one-dimensional case. Right? And now we have another term, 1 minus mu. Why? Because of this two-dimensional coupling. So this stress will be little higher. What's the value for this Poisson's ratio? It's like 30%, right? So a little bit about 30% higher. Okay. No. Well, let's say you have a case with a little bit of a thickness, this one, right? And then you apply any stress like that. As long as this stress you apply is within xy plane, then always a sigma zz, zx, and zy will be 0. Why? Because we do not apply any stress in z direction. So approximately, not strictly, but approximately, this term will be 0, even though we have some thickness in z direction.
교수님, 그러면 두께를 이소 두께로 그냥 가정하고 문제를 푸는 건가요?
Yeah, I mean the stress will not be affected by thickness. There is an Excel file for stress strain temperature relations. Just for your understanding, here is the 6x6 matrix, and here is the strain, and here is the stress, and here is the temperature. So whatever you apply, okay, for instance, this is the Young's modulus, and this is the 1 over E, right? And this is the how you make this stiffness, and you can, whenever you change the material properties, and this stiffness matrix will change. And this is the stress. Any stress you apply here will you will have strain. Okay, let me put it in a little more graphical form. Which one? Okay. See, this is the epsilon x and epsilon y, epsilon z, and 3 shear strain. Now I apply 1, 0, 0, 0. Apply 1, 0, 0, 0, 0. Then as you can see, we have tension, the tensile strain in x direction, but in y direction you have a compression. Why? Contraction. Why is that? Simply we have a body like that and you apply load, then it will extend in x direction and it will contract in y direction, right? Same for z direction. That's why we have a tension in x, extension, and compression in y and z directions, right? That's what it meant. And how about the shear? There will be no shear under tension. Where is it? Okay. Now, let me ask, what if we apply same stress in 1, 1, 1 and all 0? What kind of strain you will have? You apply 1, 1, 1. How much strain you will have? What do you mean 0? Well, material will not fail. I know it is a failure criterion. Will be all these 3-directional strain will be same, right? Because x, y, z, they are all same stress and strain will be same, and there will be no shear strain, right? And you need to calculate. You need to calculate how much you will have this much. This tensile strain. Well, you can simply calculate using this matrix, right? 1, 1, 1, 0, 0, 0, and multiply, you will have this one. Now, let's say you apply 0, 0, 0, 0, 0, and shear, one directions. And shear stress only cause that directional shear deformation. No coupling. Do you understand? Okay. And only shear stress is causing that directional shear strain. How about 1 and 1? Well, when we apply 1 and 1, z direction will contract, right? Z direction strain, we will have a contractions, minus, and x and y, we will have a positive elongation, and there will be no shear strain. Okay. Now, let me ask the other way. Now we apply strain. Now we somehow constrained, apply deformation. And how much stress we will need to cause that much strain? The problem is reversed. Okay? That was a stress and that was a strain. And now here, to calculate the strain, given strain and stress, this stress is the reverse of this matrix. Right? Reverse of this one. And let me ask, one, of course, the one, if we apply same constraint, this way, that way, then, tension, then we will have all positive stress. To have a tensional strain in every direction, we certainly need a tensional load in every directions. Remember that all strain 0, 0, 0, there will be no stress, but when we applying delta t, let's say 100, then how much we have this strain, stress, this is all compressive stress in every direction. Okay? So anyhow, key point is this equation, stress, strain equal S is 1 over S, 1 over E conceptually, plus a thermal strain. More circle program, well, we already have seen this program, and whatever you get the value, you better compare with this result. More circles. One of the interesting and important more circle is that, let's say we apply pure shear case, only pure shear case. What kind of Mohr circle we will have? Zero stress, sigma xx 0, yy 0. We only apply shear stress. What kind of failure in Mohr circle we will have? Where is the circle? Okay, here. So 0, 0, 1 means that we have a here and here, this is x, and here is y. Why? Because x point will be 0, 1. Y point will be 0, 1. Right? So this is the x and y, and then this will be the circle. And this is the Mohr circle. We are at here and there. Now in 45 directions, this is very important. In 45 direction means that this moves to there and then moves here. So in 45 directions, what is this? This is in tension. This is in compression. Very important. Let me draw that case, which is that we have a pure shear, right? And Mohr circle is as, in 45 directions, in this direction, 45 directions, this is what? Tension. This is what? Compression. This is the same as this one. Because again, the Mohr circle is as circular. And here is the X and Y corresponding this one. And in 45 directions, we do have this one. 45 means that, the 90 and theta will be 45. So in 45 direction, this one is the tension, right? And this one is the compression, this way. What's the magnitude? As you can see here, this radius, this is all same. So whatever, if you apply tau equal 1, then sigma x will be 1 and sigma y will be -1. Okay, you gotta remember this. You need to know how to draw Mohr circle, of course, and you have to have these relations immediately. You have this one, you get this one. If you look at this much shear load, let's compare the loading direction and magnitude. See, you have this much load. Do you see this arrow? This is going that way, and this is going that way. See, going that way and going that way. And this is not enough. See, this one, you need to have some kind of a push inside and push inside. So we have this one. So pushing means that compression, and this way is a tension. So this material is very weak in tension mode, like a brittle material. Then this material will break in these directions, because this one is subject to a tension mode, right? Okay, so this is a pure shear case, and again, which is a combination of one directional compression and the other directional in tension. Okay, let me demonstrate this one. See, this stress state and this stress state is the same. Okay, and take a look at this paper, and this paper is very strong in tension, right? Very strong. But how about the compression? It's very weak, right? Very weak. So if we apply shear load, and this paper, what will happen to this paper? This one will be very strong in this way and very weak this way, right? Because this way we have a compressive, this way we have a tension, right? So let's apply shear load here. Well, I need two more hands. Okay, you apply this one and that. I apply this one and that. Okay. and you hold this one. You have to apply, you have to hold like edges like that. And what do you see, this wave? Huh? I apply this way. And as you can see, this wave is this way, right? This way. Why? Because this is the compressive. I mean, this way is compressive. Is that right? Yeah, this way is compressive. So I need to delete this one. See, it has a compressive, then this wave will be like that, right? So let me do it again. And that is this one, I apply this one, and this one, I apply this. And you apply this too. Ready? So I apply it this way. And as you can see here, the wave. Do you see that? And I apply this way, and he applied that way, is a shear. And as you can see here, the paper is broken. So the message I want to give you is that this one is this way is a compressive, and that way is a tension. That is exactly the same as the pure shear. Okay? Thank you. So, see, this kind of understanding, stress transformations, again, this one and that is exactly the same stress state. Only difference is the how you look at it. So that's why you can predict how this material will fail in certain directions. So if material is very weak in tension, this one will break this way. If this material is very weak in compression, then this material will collapse in this way, right? So anyhow, as you can see, you should be able to transform stresses. Let me ask, okay, now we apply certain shear stress here, and it failed, or it yield. And this one will reach, we can call it shear strength, okay, shear strength. And we do have the tensile strength yield, and this yield and this tau yield has to have some relations. Do you understand my question? We apply just pure shear until material failed, which is called tau yield. And this tau yield, how this tau yield relate to a sigma yield, which is a tensile yield strength. How do we do that? How do we calculate this? 2 times? Yes, let me check. This one, we simply say sigma x is tau and sigma y is minus tau, right? Because this is the same stress transform. And as you can see, sigma 1, sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square equal twice sigma yield square, right? So this one, we just put it here, this here. So tau minus tau, so this is minus, so plus. And what is this? 0, 0. And so tau square plus tau square. So we have 4. So 6 times of tau square equal 2 sigma yield square. So tau yield will be sigma yield root divided by root 3. Am I right? Yeah, should be right. Okay. This is the von Mises yield criterion. Okay. Well, if you guys don't have any question, I will stop class. Okay. Well, here sigma 3 and sigma x is sigma 1 equals sigma x, and sigma y equals sigma 2. They are all same, right? So sigma 2 minus sigma 1 will be 0 because they are same. And we have a sigma 3, and this is sigma 3 are 0. And sigma x and sigma y, we have 2 of them. Okay? Well, I don't know how many midterm, previous X midterm question you have, and I recommend you go through all previous midterm exam last years, and that will help you to. Do we have them on the website? Well, most of them are Korean. Well, you go through, and then I'm sure you can find some questions which will be covered by our midterm. Okay. Again, stress, strain, and temperature relations, and stress transformation mostly are most circles, and failure criterions, and statically determinate and indeterminate. Those are key words. Okay. Okay. So see you Thursday.